Hey everybody, welcome to lesson 3.6 B. We're going to look more today at transforming linear equations. You're going to want to use graph paper for your notes today. You're also going to want to have your function notation function transformation handout handy as well to help you with this. So take a moment to set up your note sheet and pause the video and then resume when you're ready. All right, so the first thing we're going to do is I want you to put away or flip over your function transformation handout for a second. I would like you to see how much of this you can fill out without looking at your handout. We're going to keep practicing this because you're going to have this completely memorized. So this is a good chance to practice now. Take a moment, pause your note sheet, or pause the video, see if you can fill this out, and then resume the video when you're ready. All right, so as a reminder, K represents vertical shift. When it's positive, we're going upwards. When it's negative, we're going downwards. H represents a horizontal shift. When we have x plus a number, or in other words, h is negative, that means that we're going left. If we have x minus a number, which means that h is positive, then we're going to the right. That one can be a little bit counterintuitive for people at times. Negative f of x is a reflection over the x-axis. And a of f of x is, if a is greater than 1, that's a vertical stretch. And remember that it may end up being negative, but that doesn't matter. We're talking about the absolute value is greater than 1, is a vertical stretch. And if 0 is less than a is less than 1, then we have a vertical compression. All right, so check your work. How did you do? How many of these did you remember? And if you need to practice a little more, that may be a good idea. Next we're going to look at a couple examples here. So we have the graph f of x equals 2x, and g of x equals 2 times x plus 4 minus 3. We want to describe the transformations, and then we're going to graph both of these and see if we're right. So what I want you to notice here is that the one common mistake people make is they look at that 2 and they tell me there's a vertical stretch. But in fact, in this case, there's not, because the 2 was also in the original function. So the 2 doesn't apply at all. However, the plus 4, that represents a horizontal shift left 4 units. And then the minus 3, that represents a vertical shift down 3 units. So let's graph both of these and see if we can see the horizontal and vertical shifts here. So I'm going to start with f of x equals 2x. The y-intercept is non-existent, so that's 0. And we're going to go up 2 over 1, up 2 over 1, and so on. We can go down 2 over 1 in the other direction as well. So I'm going to draw these in. And remember to always put arrows on your lines, right? Because they're lines. They go on forever. So then our new function, now for our new function g of x, we need to convert this into slope-intercept form before we can graph it. So the first thing I'm going to do is distribute, right? So that gives us 2x plus 8 minus 3, which is the same thing as 2x plus 5. Now we're in slope-intercept form. Now we can actually graph this. So for g of x, we know we've got a y-intercept of 5. 1, 2, 3, 4, 5. And we're going up 2 over 1. Up 2 over 1, up 2 over 1, down 2 over 1, down 2 over 1, and so on. And it makes sense that these lines are parallel because we had no vertical stretch or compression. We just shifted. But let's check if we're actually right. If we're right, if I pick a point, I should be able to go down 3, left 4, and get to another point. So for example, if I pick this one right here, and I go down 3, 1, 2, 3, and then left 4, 1, 2, 3, 4, I would end up at that point, right? And the same thing is true. If I take any other point and go down 3, left 4, I'd end up at another point on our other line. So the red line, I could have graphed it the way I did by converting to slope-intercept form and then graphing it. But if I'd wanted to, I could have just looked at the blue line and taken every single point and gone left 4 and down 3 and ended up and plotted that point, and I would have ended up with the red line. So that gives you another way to graph. You can actually use the transformations to graph lines. So let's look at another one of these. We have f of x equals negative x, and g of x equals negative 2x plus 3. And the first thing we want to do is we want to write down our transformations. And again, I want to point out that since they both have a negative, the negative is not a transformation because it was in the original function. However, we do have two transformations here. The 2, that represents a vertical stretch of 2. And that's because 2 is greater than 1. So it's a vertical stretch rather than a compression, or what your book calls a shrink. And then the 3, that's our k value. So that represents a vertical shift up 3. So we're going to graph both of these. So f of x is negative x, so that means it has a y-intercept of 0 and a slope of negative 1. And then g of x, so this is f of x. G of x is negative 2x plus 3, so it has a y-intercept of 1, 2, 3, and a slope that goes down 2 over 1, down 2 over 1, down 2 over 1. And as you might expect here, they're going to cross because one of them is steeper than the other one. And so if I try to draw this in as best I can, this is g of x. And you can kind of see here that it's much steeper, and it's also been shifted upwards because each point could be considered a little bit higher than the other point. It's a little confusing because it's also steeper, and so the two kind of merge together a little bit. All right, so our last example here is just identifying transformations from a word problem. So I want you to imagine for a second that your cable company charges customers $60 a month for its services without charging an installation fee. So the cost to a customer is represented by C of M equals 60M because it's $60 every month. So then to attract new customers, they're like, hey, let's reduce our monthly fee to $30, but we're going to add a one-time upfront installation fee, in other words, when they start your cable, of $45. So the cost to a new customer is represented by R of M equals 30M plus 45. And so the question is, what are the transformations from the graph of C to the graph of R? And let's start with the easy one, the plus 45. Because that's outside of the parentheses, that's a vertical shift up 45. Now the slightly trickier one is going from 60 to 30. If you think about what that represents, that's our A value. And we're actually dividing it by 2 or multiplying it by 1/2. So this is really saying A equals 1/2 because we went from 60 to 30. And so that means that we actually have a vertical compression. In other words, if we were to graph this, it would get flatter. A vertical compression of 1/2. So those are our two transformations that occur when the cable company executes this sale. So that brings us to the end of 3.6b. You're going to work on a lot more of these examples tonight in your homework. So I'd recommend that you have your transformations handout with you, but I'd also recommend that you try to start doing it without the transformations handout as much as possible to see if you can familiarize yourself with the transformations.